So section 23 is on extreme values of functions. In other words, it's on maxima and minima. So finding a maximum, finding a minimum. Okay, so I tried to draw a picture that has everything you would ever need to know in this one picture. So we're going to talk about this picture first. So for the very first thing, we have no max. So why do you think that there is no max at that particular point? Because there's not really a point there, right? It's open. Does that make sense? You can't talk about a maximum being directly before the point because we don't know how to notate that. We can't say, oh, the point that's directly before that point that is open, right? We don't do that. Okay, so we just say that there's no max. Okay, we have local min at x equals b. A local min is just saying that we have a minimum, meaning we have kind of like a valley area. We have hills for maximums, valleys for mins. And it's the lowest point in that general area. So in math, we call that in the neighborhood. So when we zoom in on a certain neighborhood, exactly, we get a minimum there. I like to refer to it as Whoville. If we zoom in very, very tiny to a tiny location, that's like the lowest little point in Whoville. So we're just zooming into a certain area. So same thing here. Do you guys see why that's a local max then by the same definition? It's not the highest point on the entire graph, but in that general area, it is the highest point. All right, same idea here, local min. Now, at these local mins and maxes that we've talked about so far, we have horizontal tangent lines. We have the slope is equal to 0. The slope equals 0, each of those places, okay? But we don't have to have the slope is equal to 0. We could also have corners and cusps. So if you look up here, this is an absolute max and also a local max. So absolute means that it is the highest point on the entire graph. So see how there's no y values that are above that point? That is the absolute maximum. And it happened where f prime was undefined. Okay, there was no derivative at that point. Okay, it doesn't exist. So that can happen. At corners and cuffs, you could still have maxes and mins. All right. Again, at this point, we have no minimum because it's open. And then we say that there's no absolute minimum because this goes off forever in the negative direction. Okay, so since there's not a lowest point on this entire graph, there is no absolute min. Does that make sense? Now, this last one that we have, there's something interesting happening there. The slope does taper off to 0 for just a second. It's kind of like on the left side, it starts out to be the minimum, and then on the right side, it starts out to be a maximum. But in the middle, it's really neither. It's not a minimum or a maximum. Okay, so what we call this, so writing it out every time is really fun, is it's a critical point, but not a max or a min. So there's something interesting happening there, but it did not end up being a max or a min. Does that make sense? So that's everything you kind of need to know about this section, but all in picture form. All right, so you have some definitions below there. So sometimes you hear absolute maximum, or you might hear the word global maximum. Okay, and this happens when your y value is the highest y value in the entire graph, okay, in the entire function, or entire domain, I guess. The y value f of c is then called the maximum value. So if I say find the maximum value of the function, what I'm asking for is a y value. I'm not asking for the x value, I'm asking how high does this graph go? All right, similarly, f has an absolute min if it's the lowest y value on the entire graph, and f of c is called the minimum value. So again, it's a y value. So if I ask for the max or the min value, it's the y value, how high or low it goes. We call the maximum and minimum values extreme values or extrema. Okay, so if you ever see an AP question that says, find the extrema of the function, that's saying find all maxes and mins. A function has a local maximum if f of x or f of c is greater than or equal to f of x whenever you're near that area. That's why it's very like vague. That's why we call it the neighborhood in that general area. Similarly, f has a local min if it's the lowest point when x is near c. Okay, so you understand all of those definitions. So if I use the word local or if I use the word relative, those mean the same thing, local and relative. And then if I use the words absolute and global, those mean the same thing. All right, so in example 1, so it says find the local maxima and minima. So that's the plural of maximum and minimum. I will still mess this up. I will say maximums and minimums all the time. Don't hold it against me. It's annoying to say maxima and minima. All right, so find the local maxima and minima in the function on the left. Is there an absolute max or an absolute min? Okay, so let's start with the local. So in a general neighborhood, see how this point is the lowest in that area, and this point is the lowest in that area. So the way we write this, whenever we talk about a minimum or a maximum, we talk about the y value. So the y value is -7. So the local min is going to be -7, and it occurs at an x value of -10. So we do not write it as a point. We always write y value at x value. All right, the next one is going to be -3, and it occurs at x equals 4. And the maximum is going to be 9, and it occurs at x equals -5. Okay, is there an absolute minimum of this graph? Yes, this one is an absolute. It's also a local, and this one's a local. All right, is there an absolute max? No. Okay, so you can say no absolute max because it goes up forever. All right, so that's what we would do if there's a graph. But there's not always a graph. So sometimes we just have a function and we have to use calculus to find the maximum and minimum. Okay, so we have f of x equals x cubed minus 3x squared. So we want to find where our derivative is either equal to 0 or undefined. That's where maximums and minimums can occur. So I have f prime of x equals 3x squared minus 6x. So I set it equal to 0. So I get x equals 0 and x equals 2. Okay, these are what we call critical values, or critical numbers. So there's something interesting happening there. So there is a horizontal tangent at those points. Is there ever a place where f prime is undefined? Yeah, no, there's no denominators or square roots or anything like that. So there's never a place where it's undefined. All right, so we're going to put those critical values on our number line. So I put 0 and 2 on the number line. And I test in each interval. I want to test to see if my f prime is positive or negative. So the easiest place to test is to go back to the 3x times x minus 2. So when I'm testing -1, I'm just worrying about whether I'm getting a negative or positive. So when I plug in -1, I have 3 times -1 is negative. -1 times -2 is negative. Negative times negative is positive, right? So you're just doing that process. You'll do this a lot in calculus. All right, so if I plug in 1 gives me a positive, and then it gives me a negative. Positive times negative is negative. And then 3, positive, and positive make positive. It does not always alternate. It did in Algebra 2. It does not in pre-calc, or not pre-calc, AP Calc. All right, so we increase, decrease, increase. Does that make sense for the original function? Think about the original function. X cubed. Is that what x cubed looks like? Yeah, up. Like x cubed graphs go like this. That's exactly what ours is doing. Up and then down and then up. Okay? So if I'm finding a local max, the local max is occurring right here at x equals 0. So how do I find how high or low it goes? Yeah, plug it into what? The original. So if I do f of 0, I get 0. So I have a local max, let me say, of 0 at x equals 0. And then I have a local min of something. So I need to find it. So I have f of 2. So 2 cubed minus 3 times 2 squared. 8 minus 12 is -4. So of -4 at x equals 2. So you always say y value at x value. Okay, do I have any absolute max or mins? No. Okay, do you guys understand why? Because it's the cubic function. It goes up forever and down forever. So no absolute. And you can just say extrema, or you could say max and mins. All right, does this make sense? Not a very hard section. We've done a little bit of this before. All right, so f of x equals sine of x. So again, find the derivative. The derivative of sine is going to be cosine. So I want to find when cosine is equal to 0 or when it's undefined. Okay, so cosine is never undefined, so we're good there. So it equals 0 in 2 locations on the unit circle. So pi over 2 and 3 pi over 2. But I didn't say on the interval 0 to 2 pi. Okay, so that means I would need to do ... I would need to say and other places too. All right, so I'm going to put this on my number line, and I'm going to test in the first derivative. Now, it's a little bit tricky when you have, oops, not negative pi over 2. When you have more than one number, because you kind of want to be really careful you kind of know that it goes off in both directions. So when you pick numbers to test, you want to pick numbers that are pretty close to it. Okay, because I don't want to pick like 0, because maybe 0 is another critical value. It's actually not. It'd be negative pi over 2. Does that make sense? That would be the next one. Okay, so let's pick like pi over 4. So if I try pi over 4 into the derivative, cosine of pi over 4, is it negative or positive? It's positive, right? Root 2 over 2. If I try pi, cosine of pi is negative, because it's negative 1. All right, and if I try something a little bit bigger than 3 pi over 2, so like 7 pi over 4, okay, then that gives me a positive value. And this makes sense if you think about sine. We could probably even find this answer for sine just based on your knowledge from pre-calculus, right? Do you guys know what sine looks like? It starts at 0, it goes up, it comes down, it goes up, it goes down, right? So where are its maximums occurring? They're occurring at pi over 2, 5 pi over 2, and so on. The minimums are occurring at 3 pi over 2. What else? Or did I say 5 pi over 2? Oops. Okay, so pi over 2. What is this? Pi over 2. Maybe I can't do it with my knowledge from pre-calc, can I? Yeah, so add 2 pi. So 5 pi over 2, so 3 pi over 2. And what's the next one? 7 pi over 2. Those are our answers. Okay, how high does it go? To 1 and negative 1. Low is negative 1, right? So that's what we're doing. We find f of pi over 2, and we plug it into the original. Sine of pi over 2 ends up giving us 1. And f of 3 pi over 2, sine of 3 pi over 2, gives us negative 1. So when we talk about our max and mins, are they absolute? Yeah, they're absolute and local, right? So we're going to say absolute local max of 1. And we're going to say at x equals pi over 2. And then to indicate that I want it to continue, I write plus 2 pi k. And then I say absolute local min of negative 1 at x equals pi over 2, no, 3 pi over 2, plus 2 pi k. And then really you should write where k is an integer. So where k is an integer. Do you guys remember, if you want to shortcut that, you can do k as an element of z. Do you guys remember that shortcut? It's like the z with the extra stem. All right, so that's the answer for that one. Okay, is this making sense? All right, so a critical number is what I just talked about. It's where f prime is equal to 0 or f prime is undefined. Okay, so something interesting is happening on your graph. You could have, you know, if f prime is undefined, maybe you have an asymptote, right? Maybe there's not a point there in the first place. Maybe you have a corner or a cusp, okay? Or if f prime is equal to 0, maybe you have a max or a min, but you could also have the shape where you have, you know, a horizontal tangent for just a second. So we're going to keep these in mind. Let's change x to the 4th. That is an interesting function, but it's interesting later on in the chapter. So we'll do x to the 2/3 for that one. It's interesting when we talk about concavity. Concavity involves the second derivative. All right, so if I have x cubed. So x cubed looks like this. So it's an interesting function because the slope is equal to 0, but there is no max or min. All right, if I have x to the 1/3, that's the cube root of x. It looks like this. This is an interesting function because for a brief moment, the slope is undefined. Okay, but again, no max or min. It has what we call a vertical tangent. And x to the 2/3, it kind of looks like x to the 1/3, but the other side has been flipped up as well. So it looks like this. So right here at 0, your slope is undefined. And you can find that if you take the derivative, it would be negative 2, or it'd be 2/3 x to the negative 1/3. So your x to the 1/3 goes on the denominator, right? So it's equal to 0, or x equals 0 gives you undefined. All right, but is there a minimum there? Yeah, so it can happen. So even if it's undefined, you could still have a minimum. So minimum at x equals 0. All right, and then the absolute value of x, same idea, right? That's another one where the slope is undefined, but there is a minimum at x equals 0. So these are good ones to keep in mind. Now the AP test is going to trick you a lot, and it usually tricks you on the type of questions where it's like, Which of the following must be true? 1, 1 and 2, 1, 2 and 3, 1 and 3. Don't you hate those problems? Yeah, they're going to do those. So be ready for those. So keep those in the back of your mind. All right, so find the critical numbers of the following function. So this is not asking you to find the max and mins, it's just saying find the x values where there's something interesting happening, okay? So find the critical numbers. So we're going to set, find f prime. So I have 3x squared plus 2x minus 1. And it's never undefined, but it does equal 0. So I end up getting x equals 1/3, and I get x equals -1. So those are what we call critical numbers. Now, some of them you can just use your knowledge of polynomials. This is an x cubed function. So if you were doing a little rough sketch, you know that the max occurs first and the min occurs second, right? So the max would be at x equals -1, and the min would be at 1/3. So sometimes you can kind of use that knowledge to help you shortcut some things. All right, so the next one, I'm going to make it a little bit easier to take the derivative. So remember in chapter 2 when I told you always try to multiply things out if possible before you take the derivative. So I'm going to have 2x to the 2/3 minus, this was x to the first, so when I multiply x to the first times x to the 2/3, right, I add my exponents. So I get x to the 5/3. So when I take the derivative, 2x to the 2/3, so I'm going to have 4/3 x to the -1/3 minus 5/3 x to the 2/3. Now in these types of problems, when you have x to a negative power, you have to get common denominators. Okay, we have to find where our function is undefined and where it's equal to 0. Okay, so the way that we do this is we get common denominators. Okay, so I'm going to rewrite this function as 4 over 3x to the 1/3 minus 5x to the 2/3 all over 3. So that way I can see that I'm missing on the second one, I'm missing the x to the 1/3. Okay, so I need to multiply that on the top and the bottom. So when I do that, I get 4 minus, you can see what x to the 2/3 times x to the 1/3 is? Just x, right, x to the 1. All over 3x to the 1/3. And the reason we do that is because we're trying to find when f prime is equal to 0, but also where f prime is undefined. Okay, so it's happening, we have actually two critical values. So f prime equals 0 comes from the numerator equaling 0. So we have 4 minus 5x equals 0. So we get 4 equals 5x, so x equals 4/5, so that's one critical value. And then the other critical value comes from when the denominator is equal to 0. So we have 3x to the 1/3 equals 0, divide by 3, cube both sides, you end up getting x equals 0. Okay, does that make sense? So you always need to be able to see what the numerator is and what the denominator is. Okay. A lot of people in the past have tried to like set it equal to 0 here, and then add the 5x to the 2/3 over 3 over, and then cross multiply, which you get one of the critical values, you would get 4/5 then. But you guys see how you would miss out on the other one? So you can do that, but you would just need to say, oh, but x was equal to 0 and that. Like if x is equal to 0, I also have a critical value. Does that make sense? So that's why I usually have people get common denominators. All right, so the extreme value theorem. So this is one that is extremely important. Extreme value. So start, so you probably want this on a note card. Okay, so there are certain things that have to be true to use this theorem. So it says if f is continuous on a closed interval, a to b, then f has to have an absolute max and it has to have an absolute min on that interval. Okay, so here's an example. Okay, if I have x squared, there's no max or min. Or, well, there is a min, but no max, right? No absolute max. Okay, but if I have x squared on a closed interval, I think I talked about this a little bit the other day, on -1 to 2, what happens is you get something like that. Is there an absolute max then? Yeah, it would be at 4. Does that make sense? So if you have a closed interval, you will always have an absolute max and an absolute min every single time. Okay. That's what the extreme value theorem is saying. So if you have a closed interval, you always have to put the endpoints on your little number line. So finding extreme on a closed interval. So to find the absolute max and min, you're going to do what we just did. You're going to find f prime, you're going to set it equal to 0, and you're going to find when it's undefined. So you're finding the critical values. Okay, but you're also going to put on the endpoints on your interval. And then the largest of the values from 1 and 2 is the absolute max, the smallest is the absolute min. Okay. All right, so find the absolute extrema of the following functions on the closed intervals. Use your calculator to step graph and verify. Okay, so I'll do this exactly like we'd have to do on the AP test. All right, so we're going to find f prime of x. So when we do this, we get 12x cubed minus 12x squared. So I want to find when it's equal to 0 and where it's undefined. It's never undefined. No denominator or anything. So I pull out a 12x squared, and I have x minus 1 left. So I get x equals 0 and I get x equals 1 as my critical values. So when I'm testing, I put them on a number line, but on my number line, I am on this closed interval -1 to 2. So I put on -1 and 2 on my number line, on the ends of it. And then in between, I have 0 and I have 1. If some of the critical values didn't fit on that number line, if they weren't between -1 and 2, then leave them off. We're not worried about them. Okay, we test in each location. So if I test, -0.5, the easiest place to test is right here in our 12x squared times x minus 1. The reason is because 12x squared, always positive. It doesn't matter what you're plugging in for 12x squared. Does that make sense? Because if I have a negative number and I square it, it's positive. If I have a positive number and I square it, it's positive. So when I plug in -0.5, I get a positive out front and then negative on the inside. So I get negative. Okay? Same with 0.5. 0.5 minus 1 is also negative. And then 1.5 gives me positive. So this is where it goes down, down, and then up. Okay? So like I said before, like in Algebra 2 or pre-calc, when you guys did critical values, usually things alternated. Usually it went plus, minus, plus. That doesn't happen in AP Calc as much. Okay? What's happening here is since you have that x squared, 0 on both sides of it, it's going to be the same sign. Because it's kind of like it has multiplicity. It's listed as a critical value twice. Does that make sense? So sometimes there will be things like that that will happen. So if I was thinking about what this graph is doing, it's going down some more, and then it's going up. But I don't know how high these endpoints are going. Maybe this one's here and this one's way up here, right? Or maybe this one's lower. We don't know. So if I'm finding the absolute max, there are two possibilities. So where could I have an absolute max? At -1 or 2. Does that make sense based on our graph? So I need to find f of -1 and I need to find f of 2. So f of -1, when I plug that into the original, I get 3 minus a -4, so I get 7. And when I plug in 2, I get 48, right, 3 times 16, minus 32, so I get 16. So which one is higher? The 16, right? So we're going to say absolute max of 16 at x equals 2. All right, now the absolute min, where does it have to be? It has to be at 1. It cannot be at 0. Do you guys see why it's not? Because it goes down and then it goes down even further. Okay, there's no minimum there. So it's an absolute min of something. So if you find f of 0, or no, f of 1, I guess, what do we get? -1, right? So absolute min of -1 at x equals 1. Okay. So when you were just finding the absolute values, you actually don't have to do the number line thing. You don't have to test them. The reason is because you're just going to end up plugging them in to find a y value anyway. But if I ask for a local max or local min, you have to do it. Because you could have a minimum that's actually higher than a maximum. Does that make sense, how we could have that? It's like a minimum, whoops, didn't draw that very well. A minimum that is higher than a maximum. So maybe something like that. So when you're trying the f values, maybe this one's lower than that one. Okay, but it doesn't mean that it's a minimum. Does that make sense? So you really should do your number line thing for that. And the AP test actually doesn't even grade the number line. So if I was going to use it, what I would need to write is I would need to say f prime is greater than 0 on 1 to 2, and f prime is less than 0 on -1 to 0 and 0 to 1. Does that make sense? You have to write what you did on that graph. Okay, they don't even look at it. The graders will totally ignore it. So you have to write that information down. All right, number 2. So f prime. So we're going to get 2 minus, so 3 times 2/3 is going to become 2. So I have 2x to the -1/3. So this is one that has a negative exponent, so I'm going to have to get common denominators. So we're going to have 2 minus 2 over x to the 1/3. So I'm going to multiply the first one by x to the 1/3 over x to the 1/3. So I'm going to get 2x to the 1/3 minus 2 all over x to the 1/3. So remember, I want where my numerator is equal to 0, and I want where my denominator is equal to 0. So both of them. So I'm going to say 2x to the 1/3 minus 2 equals 0. So I have x to the 1/3 equals 1. So x equals 1. Right, cube both sides. Then I have x to the 1/3 equals 0. So when I cube both sides, I get x equals 0. Those are my critical values. So I have between -1 and 3, and I'm trying 0 and 1. So you can do the plus minus plus thing, and it will be useful, like I said, to find locals. So we'll go ahead and do it. So let's say I'm plugging in -0.5. If I take -0.5 and I raise it to the 1/3, it's still negative. So times 2 is still negative. Minus 2 is negative. All over a negative. So negative over negative is positive. If I try 0.5, then the top actually becomes, let's see, 1.587 minus 2. So it's negative. And the bottom is positive. So this one's negative. And if I try like 2, the top becomes positive, the bottom is positive, so it's positive. So it's going up, down, and then up. Okay? I always, if I have something that's undefined, now the 0 is undefined, you guys see? When I plugged in 0, it made f prime undefined. I always need to know what's happening there. Because it looks right now like it's maximum, but what's keeping it from looking like this, an asymptote? How do we know it's not an asymptote? Okay, so go back to your original. Plug it in, what do you get? If you plug in 0 to the original, you get 0, okay. What would happen if it was an asymptote? When you plugged it in, you would get undefined. There would be a denominator, right? Does that make sense? Okay, so this is not an asymptote, so maybe write yourself a note. Not an asymptote. That's always good to know. All right, so since it's not an asymptote, we actually have a point there, and it could be a maximum. So we're going to compare to find the absolute max. We have to compare f of 0 and f of 3. We want to see which one's higher. Okay, so we do that. F of 0 and f of 3. F of 0 we said was 0. F of 3 is some nasty number. Did you guys get it? I need someone to be like 2 steps ahead of me. All right, I think it's -0.240. Okay, so which one's higher? 0, right? So we're going to have absolute max of 0 at x equals 0. And for the absolute min is going to either occur at 1 or -1. So we compare those two things. Anybody have either of those? So 2 minus 3 is -1. So f of 1 is -1. And then the other one is -2, and then it's also -3, so -5. So the absolute min of -5 at x equals -1. Okay, so one last problem. So you guys understand that? So just comparing how high they are. All right, so very last problem. So f of x equals 2 sine of x minus cosine squared of x. Some of you guys are still having trouble taking the derivative of cosine squared of x. So remember, think of it as cosine of x squared. So when you take the derivative, you have f prime of x equals 2 sine of x minus, or not, 2 cosine of x, sorry. Almost. All right, 2 cosine of x minus 2 cosine of x times the derivative of cosine of x, so negative sine of x. So we get 2 cosine of x plus 2 cosine x sine x. Okay, it's never undefined. So find where it's equal to 0. Pull out the common factor, which is 2 cosine of x. This reminds me of one of your study guide problems. And set each piece equal to 0. So when we set 2 cosine of x equal to 0, and 1 plus sine of x equal to 0, cosine is equal to 0 here and here. So it's going to be at pi over 2 and 3 pi over 2. And we know we're on the interval 0 to 2 pi, so we're good there. No more. All right, and then this next one is sine of x equals -1. And that's happening right there, right? At 3 pi over 2. Okay, so like I said, you could do the number line, but since this is only asking for the absolute, what you could do is you're just finding how high or how low the entire graph goes. So you can remember that we have critical values of 0 and 2 pi as well, and pi over 2 and 3 pi over 2. And you can kind of skip the plus minus plus thing. Like you actually don't need that. You're finding how high the highest point is, how low the lowest point is. So what we're going to do is find f of 0, f of pi over 2, f of 3 pi over 2, and f of 2 pi. We're going to find each thing. So f of 0 is going to be 2 times sine of 0, which is 0, minus cosine of 0 squared. What's cosine of 0? 1, so -1, right? And then same idea for 2 pi. It's exactly the same thing. And if I plug in pi over 2, I get 2 times sine of pi over 2 is 2, and cosine of pi over 2 is 0. So I get 2. And 3 pi over 2 gives you -2. So the absolute max is going to be 2 at pi over 2. And the absolute min is going to be -2 at x equals 3 pi over 2. So see how if you're only asking for the absolute, you can avoid the plus minus plus thing. But you have to do it if you need local. So don't forget if you have local.